Okay, let's go ahead and get started. So today we will be continuing proof writing. Um, in my last lectures, I introduced proofs. In particular, I introduced direct proofs. Today we will be looking at indirect proofs. Okay, so let's start with a claim. So claim. So if 3n plus 2 is odd, then n is odd. Okay, so when considering this proof or this claim, does it make sense? So let's consider a case when this is odd. So I guess when this is equal to 5, n must be 1, so then n would be odd. Okay. If this is equal to 9, let's see, 6, yeah, let's see. Oh, 11. If this is equal to 11, then n must be 3, so then n is odd. Okay, so it makes sense. So let's consider how we prove this. So as I mentioned in my previous lectures, we have the formal proof, which I'll write on this side of the board. And then my scratch work, I'll write over here. Okay. Now, if you tried to prove this in a direct manner, so let's just suppose that we can do this. So if we try to direct proof, okay, we assume the hypothesis to be true, okay? So then we assume 3n plus 2 is odd. Okay? But then, okay, if that's odd, by definition, right, if you recall from the previous lecture, 3n plus 2 is equal to 2 times some integer plus 1, right? Where k is just an integer. Okay? But then we don't really have much to work with here. So we typically want to look at the conclusion of the claim and then say, okay, let's see if we can show that n is odd. So we got here, so then we have 3n plus 2 is equal to 2k plus 1. 3n is equal to 2k. So we should subtract 2 on both sides. We get 1. And then we get that n is equal to 2k minus 1 over 3. And to me, that doesn't, I don't see immediately how that would be odd, right? It doesn't look like twice an integer plus 1. So at this point, you might get stuck, right? If you're trying to prove this statement, you might get stuck. Well, that's when you should start considering indirect methods of proof. In particular, if you recall from the logic section that we covered, we know that if P, then Q is logically equivalent to not Q implies not P. And that's called the contrapositive. So, contrapositive. Okay, so if we look at our statement here, right, we have this conditional, right? If, so this is like, that's like our P, right? And then here, that's our Q, right? If P, then Q. Well, when trying to prove if P, then Q, if we can't prove it, like this doesn't look like, I don't know how to make that look odd, right? If we can't directly prove it, then we can consider the contrapositive of the statement and see if we can prove that, right? So let's try. So let's go and do this. And we're going to say, we're going to try to prove this by proving the contrapositive. Okay. So the contrapositive, we're going to assume as our hypothesis the negation of Q, the conclusion here. So we assume the negation of the conclusion, and we show that that implies the negation of the hypothesis. Not the conclusion implies not the hypothesis. We're going to prove that. So we assume N is not odd. Right? We're going to assume the negation of this statement here. So we're going to assume N is even. Right? All integers are either even or odd. So this is the negation of the conclusion of the original claim. That's what we assume. Then, as before, as soon as we make any type of assumption, as soon as we declare that N is even, we can use a definition. So then N must be equal to twice of an integer, 2 times an integer, right? So where K is an integer. Okay. Now, again, as before in my previous lectures, we do a little bit of algebra to get where we want. Well, where do we want to be? So we want to show that the negation of the hypothesis is true. So here, the hypothesis is 3n plus 2 is odd. So we want to look at the negation of that. Right, so we consider 3n plus 2. But that's really equal to 3 times 2k plus 2, right? And we want to show that it's even. Right? Again, I can't emphasize this enough. We want to show the negation of this, right here, is true. So, I see a factor of 2 here, so I can factor out that 2. Like that. And then I see, oh, 2 times an integer. So this altogether implies that 3n plus 2 is even. So if n is even, then 3n plus 2 is even, which is precisely the contrapositive of that claim. Right? You see that, right? So maybe I'll say like this claim is equivalent to saying if n is even, then 3n plus 2 is even. And this is the contrapositive of this whole statement. And we can prove the contrapositive is true. And if that's true, then the original claim is true. Okay? So let's go ahead and write down our formal proof now. We have our scratch work to go off of. So unlike direct proofs, when we just assume the hypothesis and continue proving, when you're using an indirect method, such as contrapositive, you need to declare that at the very beginning of your proof so that the reader knows that you're proving the contrapositive. I like to start that off by saying, by way of contraposition, assume n is even. And so by way of contraposition, we're assuming that n is even. That declares to the reader, if they look at the original claim, oh, contraposition means we're going to assume the negation of the conclusion, right? So, okay, now it's as before. So try writing down what you think the rest of the proof would be, and then I'll finish it off after like a minute. Again, you just have to fill in with words what we did here. Can anyone guess what the next sentence is going to be? Can someone tell me? So formal proof, we're at like this line right here. And so the next line of this proof is going to be what?
I guess that if n is even, then 2 times another integer k would be a value of n.
Right. So you're going to reference the definition of what you've assumed. So that's exactly what you're trying to get across here. So then we can say, by definition, there exists an integer k so that n is equal to 2 times k. So all you're doing is referencing that definition. Okay. Now, so we've got like past that. So now we're to the algebra part of this proof. So then you could say something like then 3n plus 2 is equal to 3 times 2k plus 2. And then factor out the 2. Like that. So now you just have to reference the definition again to finish off the proof, because we see that 3n plus 2 is equal to 2 times an integer. So you can say something like, since 3k plus 1 is an integer, 3n plus 2 is even by definition. And then you're done. So what this has done, this is a proof of the contrapositive of that statement. Since these have the same, these are logically equivalent, we've proven the original claim. Okay. Okay. It's not so bad. As long as you know how to translate the original claim into its contrapositive, the proofs are basically the same as what we did in the previous lecture. Okay, let's look at another one. So, if n is equal to a times b, where a and b are positive integers, then, what does it say? A is less than or equal to root n, or b is less than or equal to root n. Okay? So, right off the bat, like if you tried to prove this directly, I'm not sure how it would look. Because the only information you have is that a and b are positive integers and n is equal to the product. So starting off with that information, I don't know how you would take square roots and have any type of information about a and b. But the proof of this using the contrapositive is straightforward. So scratch proof right here. So we're going to prove this using the contrapositive. Okay. So it helps to identify the hypothesis and the conclusion. So here is the conclusion Q. And then here, that's your hypothesis, P. Okay. So then, if we're going to prove by contraposition, we assume the negation of this, of the conclusion. So the negation of that is that, so if you negate this, you have to use De Morgan's law, right? So if you negate this statement, it becomes, we assume A is greater than root n, right? And that or becomes an and. B is strictly greater than root n. Okay? So now, we want to look at the hypothesis here, in particular, this right there. Okay? And we want to show that that's not true. Like we're negating P, so we want to show not P implies not Q implies not P. So then I can say, okay, well, A times B, right? If A is greater than root n, then A times B is greater than root n times B, right? Because A is that quantity here is bigger than that quantity there. Okay? But B is greater than root n as well, right? So then this is strictly greater than root n times root n, but that's equal to n. So what we've shown is that a times b is greater than n, which is definitely not the case that n is equal to a times b. So the formal proof here would be something like, again, you have to state that you're doing an indirect proof. So by way of contraposition, assume was it a is greater than root n and b is greater than root n. Okay. Now, if we're assuming that a and b are positive integers, so if a, I'll just go ahead and use the set building notation where a, b are elements of c plus the positive integers, then when we multiply a times b, we're not going to flip the direction of the inequality. So it's going to be a times b is greater than root n times root n, which is equal to n. And then we're done. Because a times b is strictly greater than n, so it's not the case that n is equal to a times b. Okay? Okay. Okay, so that's proof by contraposition. Next, we're going to move to proof by contradiction. But because these are kind of separate techniques, I'm going to go ahead and cut the lecture here for proof by contraposition, and then I'll record another one for proof by contradiction. So today's lecture is rather short, but I will post another lecture later today on proof by contradiction. Okay? So hope everyone stays safe. That'll be it for today. Just keep on checking Blackboard or my YouTube channel, and you'll see more videos pop up. All right? And also, if you need to speak with me privately at all about anything, please just email me and we can set up a Zoom meeting and I can talk with you whenever. All right? Yes, this video will be posted on YouTube. All right, y'all have a good day.
Thank you.